Yeah.
Should we give it another honorary 3 minutes just to build up audience?
Yeah, they may not realize it.
Right. Well, we did tell them all the extra.
Yeah.
The most important thing that Zoom is it records talk. We have a record.
So in principle, you can record with your key thing.
Cut and cut. Put it in and cut it.
It will be on your laptop, and then upload it.
I discovered a new faster way to get here today. Really, I think it chopped off 2 minutes.
Why do you need a faster way?
Because, you know, I'm
Yes.
more rich and
Yeah.
Okay, so welcome back. And we're really happy to be back in the Roberts building with much more oxygen. And so this morning, Joerg is going to tell us about SYK approaches to Eliashberg theory, Eliashberg theory, and its possible, perhaps definite, connection with quantum gravity and holographic.
Yes. Yes. Thanks a lot. It's so wonderful to be here. It's such a gorgeous city to walk in the morning for half an hour. So it was great to be here. This work was done together with a number of wonderful colleagues. It started out with a paper we wrote together with Eliashberg, who back then was a graduate student at Stanford. When I visited Stanford for a while, he's now a postdoc at Harvard, and we had an enormous amount of fun during what was back then something like a 5 to 6 week stay. The more recent work that will play an important role in our today's discussion was jointly with Konrad Skalm, string theorist and particle theorist from Leiden University, and Jan Andrejenkov, who's a graduate student in Karlsruhe, and issues that haven't been yet written up, but the results are there. We're done with Veronica Stangier, a graduate student just beginning in Karlsruhe, wonderful student, and Davide Valentinas, the postdoc. So there will be 2 lectures. And what we will be discussing today will primarily be concerned with superconductivity in quantum critical systems, aka in strange metals, if you want so. And what we want to do as a specific side aspect of this one is to do a step-by-step derivation of what has been discussed a great deal in the literature during the last more than a decade in the condensed matter context, namely the holographic approach or gravitational approach to description of quantum critical systems. We will start out doing this in a very simple toy model in 0 dimensions, and then maybe only in the second lecture, but we will see how far we get to go on to higher dimensions. And then the second part will be concerned with much worse systems, namely systems where they're extremely incoherent. Often they're referred to as bad metals. We see what happens with superconductivity there. Good. As a warm-up, we saw some of those slides already, I think yesterday at least, in the talk by Sven, where we have, where he showed, I think it was cerium palladium to silicon 2. So what we're having here is the often mentioned and connection between quantum criticality and superconductivity. We see this in such chemically different materials that it's something worthwhile paying attention to. It's been pointed out many years ago. Here we have the heavy fermion systems. You have a magnetic state. You somehow, in this specific case, by pressure, suppress the transition temperature, and lo and behold, right where the magnetism vanishes, we see superconductivity. This is an organic charge transfer salt, a quasi-one-dimensional system, and the same behavior seems to be happening. This is an iron-based superconductor, and as we suppress the ordering temperature, we have superconducting transition temperature, largest right where the magnetism is vanishing. Quantum criticality, particularly in a slightly different version, in the so-called phosphorus doped, where you substitute arsenic by phosphorus, quantum critical behavior and transport was quite clearly been observed. So there is a connection in one way or another there. And it is a legitimate question that has already been addressed, but this is part of our discussion here, why superconductivity is so abundant. And before we go to discuss answers, let's understand the question in a little bit sharper way. So what we do here is we remind ourselves of the Cooper instability. So the Cooper instability in, say, the many-body language can be understood in the following way, that we're saying we have some quasiparticles. So that would then be captured by some finite residuum of a single pole in my single particle propagator, something that we usually results from a certain, say, Fermi liquid-like description of, say, scattering processes. And then we sum up particle-particle diagrams. In order to see what is the pairing response of the system, and in well understood limits of leading logs, there is a kind of geometric series summed up where the particle response of a single free fermion system enters. So we need to know what our propagator is. We do a little bit of a convolution. There's a log. This log, you can see, is directly related to the single pole here. So having a log then tells us that once, no matter how small the interaction, of course, this system will be superconducting. There's no way out. That is wonderful. Of course, the interaction has to be in some reasonable channel attractive, but we know how to deal with this. We get the Cooper instability. So now we can ask the question, what happens to precisely this discussion when we model in one way or another non-Fermi liquid behavior? This was done in the late 90s. Here, smart people were investigating this problem. What you do is, instead of taking the Fermi liquid pole, you just model just by hand. How would I describe a non-Fermi liquid state? There might be some power law behavior. So let's say there's a more singular power than linear. I have an exponent gamma being positive. And then now I'm doing copy paste. Let's not ask whether this is justified. Let's just do it first. I sum up those diagrams. I have to do the exact same thing, and I have to evaluate the exact same integral. Now here you recognize the Baire propagator and the self-energy correction. Now this is more singular than that term at low frequencies. but this makes the integral convergent. Hence, this is finite. In other words, now an arbitrarily small interaction would not be enough anymore to give me superconductivity. So this is just like the Stoner instability of a ferromagnet, right? They do happen. Maybe we don't have a controlled theory, but nature doesn't care about that. They do happen, but they are not the rule, they are the exception. Bardeen wrote a paper why sodium is not superconducting. There's no paper from Bardeen writing why sodium is not a ferromagnet, because it would be the exception to have, exceed that Stoner instability, particularly for that system, but also for many other systems. So therefore, this is what I meant at the beginning. Why is there superconductivity when you have quantum criticality? It seems to be that the quasiparticles are much less sharply defined objects. Hence, they don't want to pair. And of course, what we did in this analysis is that we implicitly assumed that the interaction is instantaneous. That's what we've done by just calling it a number. On the time scale of this power law behavior, this was assumed to be a constant, so it could be pulled out of the integral. And by doing so, well, we assumed it to be instantaneous. So we said there is something making the system critical, but we ignored the fact that the pairing interaction will have to worry about this fact and the retarded nature of the system in some way or another. And there are two ways that I know of, and certainly there are many more, in particular when you think about one-dimensional systems, but there are two wonderful ways to think about this that have addressed this problem. So it's, to some extent, at least to some communities, a solved problem. So, and they go by superconductivity by critical bosons and holographic superconductivity. Let me briefly sketch both of them and compare them with one another. Yes?
There's something quite different between these. In a holographic case, the superconductivity is critical as well. But in the superconductivity by critical bosons, the formation of the orbital parameter actually breaks the criticality.
In both cases, once you condense, you will break the criticality. So what we are doing here is we will be, and we will get to this in some detail, but we will have to assume, and for this to work, that superconductivity is a small perturbation to some existing critical state. And there are good questions. This is not always a sensible thing to do. Very often, what you find in concrete calculations, superconductivity sets on the same scale where if you were to suppress superconductivity, criticality would switch on. In that case, you don't have a regime for negotiation. So so therefore intellectually it's sharper if you can, and you can in some cases separate these scales and then argue by adiabaticity that maybe some of these statements are still true. We will also get next lecture into the issue of what happens when you actually condense with the holographic description, at least. In that case, we will find, it's a cute work at least, that the condensation of the superconductor changes the geometry of So I'm back on Zoom.
Yes.
Yeah. Okay. So RVB is a wonderful theory. I mean, I truly love it. I've done myself certain
between the metal and another B state or at the edge of a box.
Yeah. No, I didn't say this. It's just too complicated for me to make this connection. Maybe put it this way. So here, so let's back to my parentage. This is what here is. There is so the fact that we don't have instantaneous. To I think in a wonderful paper from Son when he looked at color superconductivity in due to the exchange of gapless gluons. And very shortly thereafter, there's a very beautiful paper from Artyom Abanov, Andrei Chubukov, and Sasha Finkelstein in the context of spin density wave mediated superconductivity and D-wave superconductivity. So what we have is we have some fermions and they couple to some bosons and there's some coupling constant. And this is a little bit abstract here, what I'm saying. But let's say you work hard and you convince at least a subset of your colleagues that this allows you to get some non-Fermi liquid type of single particle dynamics at some quantum critical point. In those calculations, what you find in all cases that I do know is that your pairing interaction ceases to be instantaneous. It will be a strongly retarded, singular in time or in frequency behavior. And where the same dynamics that governs the non-Fermi liquid behavior now also puts its footprint onto the retarded interaction, actually, as you see from the same exponent. It's not some exponent, it's the same exponent that enters here. So therefore the interaction, although the interaction is between less developed carriers, it is much more singular in a way that these two states really communicate with one another. These two aspects of the problem communicate to one another. And if you want so, there's almost a log back there. In the problem, and you can get something that I would call a generalized Cooper instability in this problem.
Can you give a reason for the compensation of exponents?
We will see an explicit calculation, and then we will see it a little bit clearer. But ultimately, it becomes very natural in the context where you this is a bosonic object. The bosonic self-energy, the bosonic dynamics is governed by fermions. And if you look at the fermion generalized singular Landau damping of the boson, if you want. So this comes from fermions, and that's why it inherits the fermionic lifetime. So it's Landau damping of the bosonic degrees of freedom. They are completely dominating the dynamics of the boson. What the boson initially wanted to do without coupling to fermions is become completely irrelevant. That's the physics underlying this one. This may not always be correct, but if this happens, that's what you find.
But you don't know any conserving feature that maintains the long time aspect of that.
Conformal symmetry would be the right description. So that's why this pops up as out of nothing from the SYK model. Yes, Premi. Excellent point. Of course, we will get back to some of this as we move on, but dimensionality is important and completely irrelevant here in the following sense. You need to be able to make the system quantum critical, and this, to some extent, is high energy physics of the bosonic degrees of freedom. Can you even make it critical? Suppose I have managed to accomplish this. Then there's an underlying assumption in all of these cases that the fermionic dynamics of a compressible state is local, in the sense that its frequency dependence overpowers always its momentum dependence. And if you can make that assumption, then you find this behavior. So the effective low energy dynamics appears to you zero dimensional. We will even see that this has a profound reasoning in the context of holography, where certain holographic spaces always flow to one that is local. So there's a connection we can make between these. So these are local theories in their character. The self-energy varies as function of frequency much more dramatically than as function of momentum on the Fermi surface. If you do have weak but singular corrections, then you don't quite know what to do with these theories, for example. So this is one way of looking at this problem. There's another way of looking at the problem that I never understood, period. And that is no sign of disrespect. It is simply something that was, the step was too big to be taken at once. So what is holographic superconductivity? It was pioneered initially by the late Steve Gubser, a gorgeous paper to read, and independently or at the same time, I don't care actually, by Sean Hartnell, Herzog, and Horowitz. Wonderful paper as well. So what do these gentlemen all say? They say there is, and we get back in the next slide onto this, there is a profound connection between critical systems and d+1 space dimension. One is space-time dimension. So d is spatial dimension, one is time, and I have a quantum field theory, and I can find a connection. There exists a connection between these quantum field theories and gravity theories in one further dimension. So in d+2 dimensions. And these gravity theories, at least in certain limits, become classical gravities. And then the strong coupling problem on the quantum field theory side can be characterized by classical gravity, which after all, being a classical theory, is something significantly more simple. And then you put a scalar field in this curved space characterized by some metric. The space is in so-called anti-de Sitter space. We get to this as well. And now I have my Ginzburg-Landau theory in anti-de Sitter space. That's what that is. That's what the holographic superconductor is. And now this problem can condense. And as this curved space to some extent mimics criticality of the system, something I haven't mentioned yet, it does. So then I have pairing in a critical state. At least what it accomplishes, it tells me how Cooper pair condensation can in principle take place in a system that is critical. So this is a different line. And now you can complain about either one of them. So, I mean, here, the usual objections that are perfectly well justified is this allowed? Is this controlled? Is there a Migdal theorem? Is this only perturbation theory? Bad, and so forth, right? All these things you can do. On the other side, you can say, is life really conformally invariant, something that is underlying this mapping? Is this relevant? What is this additional dimension in any way? And so forth.
I remember that Steve Gubser himself had serious worries about this approach. There were serious worries about the extensive entropy of n squared, if I remember, in these kinds of solutions, and at least until the Kitaya connection with this it led to a decline of interest in the area.
Yeah. And clearly, I mean, everybody who has done DMFT knows how extensive entropies can come about, right? Say in the Mott insulating state or something. That's the exact same physics here.
Right.
Yeah.
Get gobbled up by something that takes over like.
Yeah, but we are smart enough to know that it gets gobbled up. I mean, come on. Life is hard. If there's any way to make my life a little bit easier, I take it, even if it's not perfect. This is not perfect either.
The physics of metals is not the physics of local moments. Local moments have a low entropy.
Yes.
Get gobbled up by the Fermi surface.
Right.
So I can completely change physics. Those were the
Yes.
worries at the time. Steve Gubser himself had.
Yeah, I mean, every sane person should have those worries, right? Yeah. Yeah. We will, I mean, I did not know this up until we tried to look into this, and we will see what I will do today is to give you a mapping between these two. And so one of the goal of this talk is to answer precisely this question. Yes, let's look at, So, well, these are very different theories, and depending on your taste, you may hate them both. And then you're in perfectly good situation because what I'm saying to you will now only confirm your perspective. Because if you, however, hate one of them and love the other, then you will be in trouble, because what I want to explain to you is that they're actually very, very closely connected, to some extent, just different perspectives of the same physics. To put this maybe differently in context, let me show you a picture that I took in the hallways of the Landau Institute in Chernogolovka from a person who is my absolute hero in theoretical physics, Lev Petrovich Gorkov. So when we start from a microscopic theory of superconductivity, then we have clearly in mind for conventional superconductors our BCS theory. But before already, Ginzburg and Landau were able to give us a phenomenological insight, super powerful, being able to explain such a variety of complex physics that to some extent it's completely irrelevant to the practitioner of the Ginzburg-Landau theory to know that there's an underlying BCS theory. Who cares? It's good enough to me. Why do I care, right? So therefore, for those subset of the community, it wasn't particularly important that Gorkov was able to draw direct connection between the microscopic theory and the Ginzburg-Landau theory. However, there are very, very important aspects that were revealed by Landau's ability to derive Ginzburg-Landau theory from BCS theory. For example, we know now what is the effective charge of the object that is characterized by the psi of Ginzburg and Landau's psi theory, how Ginzburg called it. And Ginzburg himself said later that they wrote in their paper that there's no good reason why E star should be different from E in Ginzburg-Landau's paper. And the reasoning for Landau's hesitation to keep it an open parameter was an interesting and a deep one, as always. And the statement was, well, if the electrical charge were to be allowed to be different, just like the effective mass, then maybe it could also be space-dependent, like the effective mass. But a space-dependent charge doesn't obey gauge invariance. And then it wouldn't make any sense. And of course, there's a topological reason underlying this factor 2 there, really, and not that we don't have in the effective mass theory, and therefore this factor 2 is perfectly allowed. And I think this alone is already deep insight and justifies all of this. So what Gorkov already also said, he also told us what is the scalar field that we have to deal with. And the scalar field is given by the equal space or equal time anomalous Green's function of the problem, where given here, of course, taken with the appropriate ensemble, so it's not vanishing, taken here, for example, in imaginary time formalism. Let's go through the arguments, because we will need this as we go along. So we have positions and time, and it's sensible to do this in the following way, that we look at center of gravity positions and time, and relative positions and time that I choose to Fourier transform. And of course, the first one, that's very important when you want to look at inhomogeneous states, at vortex physics, at what Pascal was looking at, if you want to look what happens near an impurity and so forth. If you want to do non-equilibrium dynamics or collective modes of the Cooper pair, then you need to look at the center of gravity time, the frequency that belongs to it, whatever you wish. The internal structure of the Cooper pair is characterized by the relative variables. So the momentum tells us about something, or whether it's a D wave or an S wave superconductor. And the frequency tells us about the internal binding processes of the Cooper pair. That is what you see in the SDM experiment when you want to see the little wiggles where you can see the footprints or the fingerprints of the, say, the phonon or whatever binds the system in the tunneling spectra. That's this frequency, not that one, for example. So all of these variables in different contexts are important, and we will get to play with them. So what we will do, and let me just give you the answer of this talk right away. What we will do is we will start from a many-body Hamiltonian, and then we will show that there's a direct connection between this anomalous Green's function that we've just had. This is now the center of gravity and the total time, and to a new variable, and where we will see that the additional dimension that makes up the system, living in not D+1 but D+2 dimension, has something to do with the internal frequency or internal space-time, depending on whether we have a Lorentz invariant or non-Lorentz invariant system. There will be differences, and the other variables just carry over. So this internal dynamics will determine the holographic variable, and all of this scalar field then indeed does sit in an anti-de Sitter space D+2. We will recognize the metric, and by this we will then be able to make a couple of statements that the effective charge is also 2. That will not be surprising, that we have an interpretation of what this holographic dimension is and how it comes to having an origin of gravity in the system. So a few more words for us to get slowly acquainted with all of this on the holographic side of the problem. So again, I mentioned some of this already. You have a quantum field theory that lives in D+1 dimensions. And this is, of course, my caricature condensed matter physicist perspective of this. Started by a number of incredibly smart people and carried over in the condensed matter context by equally smart people. We have a statement that the partition function of this field theory can be written down in terms of a gravity theory that lives in some extra dimension. And the way we have to look at this, we look at this from the side, and this is our extra dimension. And this is really where the curvature takes place. In this extra dimension, there's a physical statement that this variable, this additional variable, has a character of a renormalization group scale or some, energy dependent scale, where this is the physics of the boundary, where we are in the actual field theory, and then we are flowing into the infrared. And if the system is at finer temperatures, we know that quantum critical RG flow stops, and the stop is here being provided by geometry, and there is a black hole placed there, and so forth. So that is the statement, and this sounded absolutely gorgeous to me, but it was not something that I could understand. I've seen many talks on this one, particularly in the early days, and the condensed matter community was exposed to this, and the experts in the field would always say, well, yeah, there's a dictionary. We just had that discussion yesterday with Andy, and well, the dictionary didn't help me. If I wanted to know why this dictionary is a good one. So on the superconducting side, maybe one more time, we already discussed there is this Ginzburg-Landau theory. So this theory here then has a gravity part, maybe as a gauge part if it's charged, and there is what we will be focusing on, a scalar particle sitting in this geometry. And usually there's a statement that near black holes nothing should condense, but this is not true for these anti-de Sitter spaces. And therefore, this mass here, when it's negative and reaches a certain bound, which in the literature goes under the name of the Brighton-Lohner-Friedman bound. So there's a certain bound below which the system will then condense. So this is what was pointed out in this context. Interesting statements were made, what happens when you charge it, and so forth. So this is holographic superconductivity. So what is an anti-de Sitter space? It's always easiest to look at this, and the easiest anti-de Sitter space is ADS2. And if I use imaginary time, Euclidean time, it's even something we can look at. It's hyperboloid that I'm drawing here in 3D space, and that can, of course, be parameterized this way. And there's a very clever parametrization of these 3 coordinates, which goes under the name of the Poincare map, where I have a variable that will play this time of tau and the variable that plays our holographic variable very naturally. And this is the mapping. You can trust me that it obeys this condition, and therefore it's a faithful, even though not complete representation of all options. And so then the geodesics in the problem are semicircles in this process. And if I draw it back on the hyperboloid, that's how it looks like. It doesn't help you a whole lot, except that it covers the hyperboloid, and that there's some symmetry broken, which makes sense because one coordinate is treated different than the others, right? The metric that comes with it has this 1 over zeta squared here. This is where all the curvature of the problem is hidden in. If it was Lorentzian time, there would just be a minus sign here in front of the time. I have imaginary time, that's why there's a plus here. If I were to have de Sitter space, which, so this is the solution of a homogeneous solution in higher dimensions of Einstein field theories with a negative cosmological constant. If you were to take a positive cosmological constant, you have so-called de Sitter space, so you have a minus sign here. Now we are in 2 dimensions, and every reasonable book on gravity or general relativity tells you in 2 dimensions there is no, if you write down the Einstein-Hilbert action, there is nothing there. There is no gravity. What you need to do is you need to generalize gravity in a sensible way. Something that was done by Roman Jarkiv and by Teitelbaum, where you basically look at this gravity as a limit of some higher dimensional space, and you look at the 2-dimensional sector of it, and then you can still make sense of it. So we want to look at scalar fields in this entire de Sitter space. Now I'm going from ADS2 to ADSD+2, and all I do is put the time I add in here in this case in Euclidean fashion, and otherwise if there's a minus sign in Lorentz invariant fashion, the spatial coordinates. I still have my curvature encoded in this additional dimension up front here, and that would be the metric for ADSD+2, D plus 1 plus 2, right? That's where it comes from. And if I now look at the scalar field, the one that we have written down, and you want to be concrete, then you just insert this wonderful and covariantly written version for a 0 gauge field, and this is how it looks like. So you have an integral over this additional dimension that goes from 0 to infinity at t equals 0. There's the usual Matsubara sum and momenta that we all know, and then you have an action here. And this action is interesting and can actually be analyzed. And the easiest way is you just look at the equation of state or the stationary equation, which would be the Klein-Gordon equation, which is a differential equation, a second-order differential equation. That's what you get from the Euler-Lagrange equation. We will see this equation later. That's why it's good to us. You don't need to remember clearly, but this equation exists, and it's nothing that is incredibly hard for us to accomplish. Another statement is to get a little bit of a sense what's going on. Let's go to Q and omega equals 0. So let's look at static and homogeneous solutions that only live in this additional dimension. If they do so, then the rest of the problem can actually be diagonalized very, very easily. You can diagonalize the entire problem, but it takes a bit more work. And what you do is you up to a power law, you do a Fourier transform in logarithmic variables, or so-called Berlin transformation. And in these new variables, I call them psi z here, the action after a few steps takes this form. So it's basically coupled oscillators. So now we understand it. This is, say, the stiffness in the orthogonal direction, governed here by the zeta, but it's just basically the log of the Fourier transform variable. And then the mass has to be more negative than this value in order to cause an instability. And that's precisely this Breitenlohner-Friedman bound that I mentioned earlier. So the hyperbolic space stabilizes a system of 0 mass for a little bit longer, and you have to have exceed a negative mass in order to make the system stable. So the geometry stabilizes the state. Okay, this is mostly, I thought I'd give some more details so we're not getting so scared of these words like geometry. They're all things, all you need to do is to lock your door and take a pencil, and then this is not beyond our ability. Of course. Yeah. No, interestingly not. We will see. Yeah, very good point. This is only, so this is a very good question from Ilya. He says, well, this is only if I formulate my problem in this way, I see Piers, that's very nice, but I see him anyway. So if you are able to formulate our problem this way, the question is, does it really only describe one critical exponent, right? Characterized, say, by some power law here or so, right? And the answer is no. The mapping itself will cover an infinity. of different universal exponents that all map onto the same action. So now the model that we want to use in order to understand the connection, I've just discussed a little bit of gravity for the reasons I just mentioned, is the Such-Hive model. We don't want to actually solve this model here. We need to solve a version of it that's a little bit different, but this is a useful starting point. And of course, it is a beautiful and at the same time a ridiculously simple model. So what is it? You have some flavor degrees of freedom, I from 1 to n. Think of it are internal quantum numbers or lattice sites. It's up to your perspective. It doesn't matter. And there is some chemical potential. There's no kinetic energy. All you have is non-local interaction energy. And this interaction energy is assumed to be random. And it's an all-to-all randomness. So every site interacts with every other site. And that's why it has to be tamed as usual by some smallness up front, because otherwise we would have a non-extensive total energy of the system. This is a Gaussian distributed random interaction, and it has a mean squared of u squared, and a mean 0 and a mean squared of u squared, or j squared, how it's often called. So now from here, this problem is solvable. It's so simple, but it's solvable, and it's not entirely trivial in its solution. And the way you solve this is actually copy pasting the logic that goes back to, I think, Bray and Moore in the context of the random transverse Ising model, where you do certain replicas, you introduce replicas to do the averaging, you decouple certain higher order interactions that result as a consequence of replicas, and you introduce something like bilocal fields. So you have lots of fields, but they all depend on 2 time variables. So here I've now done a shortcut. Just because it would go a little bit into another digression. But what you can do in this approach is that you write the partition function as an integral over collective fields that depend on 2 time variables. And you can then write them very neatly in a way that on the saddle point, these 2 objects that have the name G and sigma indeed become the single particle Green's function and the corresponding self-energy in obey. This is one saddle point equation, a Dyson equation. And the other one, so this is the Dyson equation here. And the other one is something that you can even write down diagrammatically as some self-consistent second order theory. So this is the effective action that you get. And if you do the saddle point of it, you get these relations, right? So we could have solved this equation before. This is second order perturbation theory of a problem with no kinetic energy, where perturbation theory truly makes no sense because the non-interacting part is 0. So therefore there are, and it depends a little bit on whether you use this as a tool to justify equations, or whether you think there's deep physics in the randomness here that gives you basically lifts frustration in the system and allows you to have, say, non-ordered states if you were to go to lattice systems, or alternatively, there's some hidden physics behind those degrees of freedom that are random, that are soft modes that allow you to describe some physics that is otherwise not accessible, or you don't know what it really is. The beauty is these 2 equations are easy to solve. And if you make the additional assumption that this self-energy is a solution of the type that I showed you earlier, but is more singular than linear, then it will always overpower the derivative, at least at low energies. And in this case, you can find an analytic solution. And the analytic solution is that the propagator has a power law behavior. Again, this goes back to this pioneering paper from Such-Hive and Ye. There are really, really important follow-up works by Antoine Georges, Olivier Pacolet, and Subir Such-Hive. And of course, there's the gravitational context was pointed out, I think, in a paper in a branch cut singularity in my Green's function. So I want to have a non-thermal liquid state, and usually we have to work very, very hard to get this. I don't want to work very hard. Yes. Oh, the sound is gone. The sound is back. Very good. So, sorry. Yes. So this is, I looked at this as just a tool to provide me without any work a non-thermal liquid solution. Because when I saw this picture or a picture like this in a talk given in Karlsruhe by actually Dima Bagretz, who came from Cologne and gave us a talk, I asked myself, so what happens when I make this thing superconducting, right? So here I have a normal state spectral function that's clearly wonderful and the branch cut, and I want to know what happens when this object becomes superconducting. And that led to some of our discussion. Before we go there now, already a first comment on the gravitational connection between the two, which is the following. The solution I've just given to you of these equations, let me go back. These equations have not just this solution that I'm giving you here, but they have actually infinitely many solutions. And all these solutions can be connected in a very simple way if I take the time variable in the problem and reparameterize it to a new function of time. Then I can construct out of one solution immediately another solution if this function only has to be monotonic. Then immediately I can construct another solution. So reparameterization invariance of the problem. It's actually something that also was discussed quite intensively in the context of glasses. So this, of course, you may or may not change the boundary condition of your solution this way. And for example, this is a very, very easy tool if you want to have the zero temperature solution and you want to construct yourself a finer temperature solution, where you just make it such the new time variable has the proper boundary conditions from 0 to beta. And then immediately if you find a temperature solution, construct it yourself, right? So so then you ask, well, if I've got infinitely many solutions, which one is the right one? And the answer will be given to you when you come back to this initial term here and include UV physics if you want so. At the UV scale, this term here will distinguish between different solutions and tell you which one is the right, and actually the one that's most simple at t=0 is exactly the right one. So, but it's UV physics that picks you the right solution. So therefore there is an energy penalty of one of those reparameterizations over another, but it's really controlled by something that would be disappearing if the upper cutoff of the theory were to vanish. So therefore, you can write down a nonlinear sigma model of all those penalties. And this nonlinear sigma model is a bit of a version that, at least to people who are not perfectly familiar with conformal field theory, is given by so-called Schwarzian derivative, a conformally invariant derivative that is an effective say nonlinear sigma model of this problem that picks the right solution at lowest energies and gives you the fluctuation expenses that you have when you reparameterize time. So why is this interesting? I mean, this is the right collective mode theory, or captures at least a significant portion of the relevant collective modes. But also the earlier mentioned gravity theory in 2 dimensions that you need to furnish with some memory of coming from higher dimensions, so-called dilaton fields, as introduced by Jacquif and Teitelbaum, has exactly the same action. So this is the quote-unquote Einstein-Hilbert action for enter-de Sitter space 2. It is a bit weird because it only depends on one variable, and that's because this funny gravity theory only is a surface theory. And so which is rooted in its quote-unquote topological character, right? But this is the gravity theory of an ADS2, And this is the action for the Satyevsky-Kitaev model. And this, of course, has led to enormous amount of discussions and cross-fertilization between the condensed matter theory and the string theory holography community, because there is a microscopic realization of something very interesting, or there are, say, gravitational concepts that could be interesting for some of these aspects that interest us.
You write this with an explicit second spatial coordinates as well.
Yes, you can, and then you can show that these after appropriate partial integrations, you get, this is a term you can't get rid of, and the other terms basically only tells you about the genus of the manifold that you're looking at in not topological terms. Yeah. Yeah.
Could you please tell us again what's going on with time here? Because last year, of course, we don't have time.
Yeah. Mm-hmm. Oh, these are configurations. Many of these configurations are not. So if you look, consider the time translation invariance as a property, maybe by your assumption of the saddle point, but the collective field won't necessarily be time translation invariant. The saddle point may or may not have that. Depends on which boundary conditions you place on it. But so this one clearly does, but others don't have to. Here I chose one that did, indeed. Exactly, it does. It doesn't have to. Yes, very good point. Yeah. Okay, so now this is the model that we want to study. But now we already used to it a little bit. This is what now goes under the name of the Yukawa-SYK model. So it is very, very simple. Again, we have these, we have added spin, but we have added spin not in any relativistically relevant way, but we just added, there is another variable that can be up or down. So in the good old fashioned matter perspective of looking at spin, we have here a chemical potential, no kinetic energy, and we add Einstein phonons to this one. The Einstein phonons have a finite mass or frequency, right? And now we let them couple phonons, whatever you want to call this boson, couples now to these fermions with a random electron phonon interaction. That's the model that we wrote down. There's a supersymmetric gauge version that is relative to this one that was discussed earlier. Yushang Wang at Florida, at Gainesville, had, at least for the normal state, the exact same model written down. This was actually quite interesting. I was at Stanford and wrote down equations on the blackboard. And one day I come to work and somebody had written my equations on the blackboard, but it wasn't my handwriting. And it was on that day, Yushang also joined, became my office mate, and must have told his calculation to somebody. I don't even know who. And it was such a weird impression, because somebody writes it's my equations, right? He wrote the one, and this was, I mean, except for certain symbol names that were different, it was exactly the same story in the normal state. So completely independent, wonderful work. In his treatment of superconductivity, superconductivity is a higher order correction effect. That's where we differ. There's a work from De Bungeon and in Eris, where they looked at purely fermionic couplings that could give superconductivity. And this model was extended to finite dimensions, and I will discuss those extensions. There's one important one from the Berkeley group. They looked at Dirac systems, where on each lattice point of the Dirac system, you have basically such a model sitting. And there's a version from Ilya and Avishkar and collaborators on compressible systems with a Fermi surface. So all what we are doing here can be generalized and was generalized, and therefore the superconductivity then was generalized by us to these situations at finite dimensions. For the time being, I stay in silly 0 dimension. So now it's technical, but we are working our way slowly forward. So these electron phonon directions are random numbers. And it actually turns out you need to think a little bit what's the right ensemble. of those random numbers. So for given k, for given phonon, this is a random matrix in single particle space. And it turns out, if I make these systems distributed in ij according to a Gaussian unitary ensemble, it breaks time reversal symmetry for every individual realization. And the implication is that the system will never be a superconductor, because time reversal symmetry broken configurations are not good for superconductivity. Alternatively, if I choose or draw these coupling constants from a Gaussian orthogonal ensemble, so they're real numbers, right? Then I get superconductivity. And because these phonons can induce superconductivity. And by this, we cooked up a distribution function where we can interpolate between the Gaussian ensemble or orthogonal and the unitary ensemble. And you can call this pair breaking. So we are titrating somewhat time reversal symmetry breaking configurations. And the reason is related to what Andrew Green was earlier asking, namely, we want to have a transition temperature that's small. And with such a parameter, I can kind of suppress my superconductivity and go to a superconducting critical point where intellectually things are clearest, and then go from there. So with this, we can just repeat what was done in the SYK model in its original fashion. We introduced replicas, we integrate out fermions, we obtain bilocal fields, but now we also get, in this specific problem, non-trivial equations and we have to introduce so-called anomalous Green's functions, so pairing fields and pairing self-energies. So there is a sufficient and a number of fields in the problem, but we've lost fear of those things, and in the end of the day, you take the saddle point. I don't bother writing down the entire action because it's just lengthy, but doesn't really tell us a whole lot. But at the saddle point, the first information that you get is you can again have a perturbative interpretation of the resulting equations and express them in diagrams, just as we've seen the second order diagram for the SYK model. And here in the large n limit, we find that the equations are just the good old-fashioned coupled Eliashberg equations. So we have a self-energy, and of course the system has no kinetic energy. That's why it gets non-thermal liquid solutions, right? But you have at large n, these Eliashberg equations are the exact solution of the problem, whatever that entails. So you have a boson propagator that gets renormalized by fermions, and you have a fermion propagator that gets renormalized by the electron phonon coupling. These are all well-known equations to people in the superconductivity community. You have an anomalous, and you have a normal Green's function, self-energy, and so forth. And then you solve this problem. You can do this analytically, and you can do this. Alpha is hidden, alpha is hidden here. Here. Sorry, that's a very good point, yes. And it's hidden here. There's a 1 minus alpha here relative to that one. Yeah. Yeah, the arrows go here in the same direction, and here they go in opposite direction. Here they go in the same direction, here they go in opposite direction. That's absolutely not visible. I have to do this better, yeah. So these are the anomalous parts, and this is the FF and the GG part, and so forth, yeah. So we can solve this problem, and let me solve it first in the superconducting, in the normal state only, to get an understanding by either ignoring superconductivity or using an ensemble where there is no superconductivity. And then you find something very, very similar. You find, from what we know from the SYK model, there is a power law solution. I just now use an exponent gamma here, mostly as in order to get the same notation that we had earlier. There is these power law solutions for the propagator of the fermions G, and for the bosons D, and well, they are singular objects. It's more maybe intuitive to see what they look like in their spectral functions. There's branch cut behavior here. And here I've shown for imaginary part of D, different temperatures. At 0 temperature, it's a blue curve. It is just singular, and then temperature cuts it off and makes it and heals it. There is a low temperature regime in an actual phase diagram where we have this quantum critical phase. The reason why we have here a phase diagram is because we have two quantities of that carry unit dimension. One is the coupling constant, appropriately formulated, and the bare phonon mass. And therefore, I can therefore take the ratio and have a dimension as coupling constant. And there's a regime where the interaction is irrelevant. There's a low temperature regime where we have this power law behavior. And there's an interesting regime that we might discuss tomorrow, but not today, where we have even different behavior. So let's stay in this low temperature regime here. Another interesting aspect is, how could it be that you always get a critical solution? And the answer is that whatever you do, the fermions renormalize the phonon mass to make it completely soft. So the effective boson mass at T equals 0 is always 0. It precisely renormalizes itself to 0 in an extended regime of the phase diagram. My interpretation for this is that the compressibility of a system that isn't a non-Fermi liquid is singular. So the non-Fermi liquid solution is just a completely natural solution, and the system does everything to get there. And that implies in this case that it has to make these phonons soft. So here we would have, if you wanted, so we would have a system where electrons would make the lattice arbitrarily soft, and then we have optical phonons that have a frequency that goes to 0 as T goes to 0. And now we add superconductivity to the problem, and then there is a regime at lowest coupling constant of this dimensionless coupling constant where the superconductivity goes basically with the same behavior than what we see is the crossover temperature. That's again the discussion we had earlier. Here we see that superconductivity sets in when non-Fermi liquid behavior wants to set in. And that's why we have to introduce pair breaking, and this is the pair breaking curve. So with pair breaking, we can suppress the superconductivity in the system. So what we have here is a toy model as simple as possible. And the toy model allows us to get superconductivity in a mean field fashion and tune it and have superconductivity of a non-Fermi liquid, and even tune it with sufficient amount of pair breaking to a point where the superconducting transition temperature becomes arbitrarily small. And now somebody needs to tell me how much time I have left. 15 minutes. Yeah. Okay. So this is of course in its global behavior the analogous of the pair breaking curve by Abrikosov and Gorkov. TC goes down if you pair break. It has a different behavior, and it actually ends at that critical point in an essential singularity. So it ends at this point in e to the minus d over the square root of alpha minus alpha critical. Alpha critical is of order 1 here. So this is something that occurs quite often in problems that spontaneously break conformal invariance. There's actually a quite beautiful paper by, I think, Pavel Koftun and Dempson, and I'm unfair to the third collaborator because I don't remember the name. It's called Conformality Lost. And there are all kinds of scenarios by which it's been explained that this type of behavior happens when you break conformal invariance, such as a Kosterlitz-Arls transition, where this is the temperature and the flow equations are being shown to be of the same type. And this is something that happens very often in holographic models in the de Sitter space ADS2. So when we saw this coming out of this model, we felt now we really need to see whether we can describe the superconductivity in a way that maybe makes direct contact to this holographic description. So you can ignore all of this if you are interested in a specific material because the model is too simple, but the technicalities or the technical aspects are easy enough so that we can make some progress and now go the next step and try to see whether we can make connection between what I talked first, the scalar field in a curved space, and these toy models. And the first statement is that you look at and this you can, near this point, I can do the following. I can go to T equals 0 and can linearize the gap equation, right? Here I can linearize the gap equation at any finite temperature, but I can go to T equals 0. and so on. And that makes it just technically easier. And if you do this, and if temperature is very, very small, I can just use it as a lower cutoff. I have a linearized gap equation. And now you see why I use those exponents. This was our earlier self-energy that made the integral so much less singular that there was no Cooper instability. And in addition, however, there is now the more singular pairing interaction. This is the boson propagator, if you want. So this is the fermion self-energy. And you see these two powers come and balance one another. And there was, so if you have a dimensionless coupling constant, and if nothing depends on cutoffs, this is essentially the only contribution you can really come up with. So this is a nice integral equation, and that is the gap equation of this SYK model. But it's an equation that is very well familiar to some people in the community because, and it was recently been in great detail studied in long and detailed papers by Chubukov and Abanov and Wu, goes under the name of the gamma model, which now explains why I use the letter gamma. So this is not just the gap equation that comes out of the silly model. It is also the gap equation that comes out of a number of problems of compressible systems that have local, by assumption or by some justification, local self-energies. And there's a long list of papers that goes over the decades where you get very similar superconductivity description than this SYK-based model would give you. In all cases, the locality there is for different reasons, but it is local and therefore only time dependent. And it is important for me because it tells me that the physics that we are capturing here is a bit more general than that of the model that we set out to capture it for. And then you have an integral equation. And at least in some limit, namely when this is a smooth function here, epsilon minus epsilon prime, if this is gamma is small, that's a very weakly dependent function, then I can essentially split the integral in two regimes where epsilon prime, the running variable, is small or larger than epsilon, and then treat the integrand that actually epsilon prime is large or small compared to epsilon. If you do this and you do something like 5 more steps, you can map this integral equation into a second order differential equation. And in addition, also, the integral equation tells you what the proper boundary conditions, of course, are. And so we have a second order differential equation for the anomalous self-energy in some limit. And yes. Yeah. Oh, very good point. So we did a large N theory. I should have been more precise. We have N fermions and M, like Marta, bosons. So you have, and when you do a large N, large M, you can vary the ratio. And that will vary the exponent gamma. It actually varies it between 0 and 1. And yeah, so there is, yeah, that's N equals M precisely. Yes, thank you. So we have a second order differential equation, and gamma is something that we know from the solution of the normal state. That's maybe also important to keep in mind. We have always the solution of the normal state. I assume I know my normal state. It's critical. Now I look what happens with superconductivity. Now I'm seeing the second order differential equation, and I showed you earlier another second order differential equation, namely for a scalar field in the radial direction of a scalar field in anti-de Sitter space. And well, if you have 2 second order differential equations that allegedly describe similar physics, it makes sense to check whether they can map one onto the other. And that's something that is easy. And indeed, you find if you construct a scalar field as function of a new variable zeta, and the new variable zeta is nothing else but 1 over the Matsubara frequencies of the relative time of the 2 parameters in the anomalous self-energy, and you furnish it with some exponent that is different for different universality classes. Independent of gamma, you find an equation that looks like this. Gamma only determines the mass of that scalar particle. It doesn't determine the equation. So that's where the answer to your question is. Different universality classes only give you different masses of the theory. Something I just would never have guessed. Probably people who understand this structurally deeper did. And this is indeed the anti-de Sitter 2 version of the equation of the Klein-Gordon equation, of the static Klein-Gordon equation that we looked at earlier. So this gave us a first hint that there is a connection, that we should interpret the new extra dimension as the internal structure of the Cooper pair in time space. It happens to be 1 over the frequency. And that therefore by going into different directions in the say, bulk direction of the anti-de Sitter space, we're probing deeper and deeper the low energy physics of the Cooper pair. While this Cooper pair may still depend on other variables that we've all suppressed here, either by assumptions because it's an SYK model or by looking at, say, equilibrium solutions only. But at least we have some idea that there is a connection. So what we see is that we can make we have our anomalous Green's function that depends on 2 time variables. We Fourier transform this back to relative time, the one that we've just done, but we can also allow it to depend on total time. And because in our action, that's perfectly possible. And then we expand our SYK model up to Gaussian order. So there are, if you look at this for a little longer, you recognize some of the terms. These are all Gaussian terms that you can get. One is the exchange of particle-particle diagrams. Much the same what we saw in the very first or second slide, where we saw we have to geometrically sum up these diagrams. And of course, this is the normal state inherited particle-particle propagator with the exact same less singular behavior that we have already encountered for non-Fermi liquids. But this particle-particle excitation is exposed to a retarded singular interaction that is singular and governed by the same exponent, because bosons and fermions are governed by this one soup. It makes no sense anymore, really, to distinguish between the fermions and the bosons, the phonons and the electrons in this system. It's a strongly coupled state. And therefore, we have a singular pairing interaction. So this is our Gaussian theory now. We have a hunch what the map should be like. From the static Eliashberg solutions, we have the Gaussian action. So the next step is to just make an identification on the level of the action and to recover the anti-de Sitter space action. And for this, the natural guess would have been to take the same power law. I call this here Z, not zeta, for reasons that we will see right away. So we just say, well, this is now a time-dependent action. But otherwise, we take what we've just learned from the Eliashberg theory that told us that there's just a power law connecting these 2 quantities. And now I'm taking F instead of phi, and therefore the power law has a different sign, but that's not important. It's the same physics. And then you get something that looks promising, but is not the answer. It looks promising because it has a wonderful geometric interpretation. Here, I can write the action that we've just seen that looked arguably a little bit ugly. Let's look at this again. This is supposed to look ugly. Here, this action down here is condensed matter physics ugliness. And now we can write this in beautiful geometric meaning with a metric and with covariant derivatives and so forth. But the metric, unfortunately, is not our anti-de Sitter metric. It happens to be actually a de Sitter metric, right? It has a wrong sign there, and these wrong signs are all marked with minus signs. And it's even more tragic. Ignore all the holography stuff. There's a minus sign here. That means this is an unstable theory, right? It can only be rescued by proper boundary conditions on the level of the Gaussian theory or by nonlinear terms or high order derivatives, right? And it is because the boundary conditions of the problem are significant. But for the time being, we have this action and we are sad, very saddened, because we have not accomplished what we wanted to do. We have not managed to map this problem onto the anti-de Sitter space. And this is not anti-de Sitter space. This is somewhat similar to de Sitter space, and everything is bad. But then you realize that there's a group of smart people on the particle physics community that told us that there's something that goes under the name of kinematic space. The kinematic space is if you are in a certain space, let's say you're in enter de Sitter space, and you can draw an enter de Sitter space geodesics. And each geodesic can be parameterized by a set of parameters and builds its own space. And it's actually a space with its own geometry. And it turns out that our de Sitter space, the one that we live in, our SYK model lives in, is the kinematic space of the enter de Sitter space. So two events here are close if in enter de Sitter space their geodesics are close in some sense. It turns out if you use this, you can then the way you transform the fields according to this goes by what is goes under the name of a Radon transformation. So you have this geodesic here parameterized by 2 points, and if I integrate the field in the enter de Sitter space over a geodesic, I get a new function that is parameterized by the geodesic, and that goes by the name of the Radon transformation. We all need Radon transformation when we want to reconstruct, say, our tomography picture from the X-ray tomography in the hospital. It's not geodesics; it's just straight lines, but otherwise it's a similar transformation. And if we then do this. So we add this Radon transformation over these geodesics. Here, this is the geodesics semicircle. It's a simple problem. Then the new action is in fact really the enter de Sitter space. And if we do this, we do get reproduce the holographic action of a superconductor in enter de Sitter space. And everything is fine. And it's just that the Radon transformation gives us fields that have much more natural boundary conditions in the UV, as we will see when we look, for example, at susceptibility. So it's not really unstable in the sense, it's a scary thing to only look at Gaussian theories without knowing what their boundary conditions are and what are the natural fields that you have to couple to them. This might be the moment when I can stop, or I can go for 3-4 minutes and I can finish it more cleanly. Yeah, is that okay? So if modulus is Radon transformation, which is to some extent now a technicality, we can, and that's actually quite cute, connect all these different terms in our original quantum mechanical action to terms as in they appear in the holographic theory. So the particle-particle fluctuations give us dynamical phenomena when there are dynamical pair interactions, and this gives us the second derivative in time. The non-local interaction of the boson gives us a gradient in the radial direction. And both terms contribute to this mass. This term always comes with a positive contribution. It doesn't want superconductivity. That's what I said earlier. Superconductivity is not the natural state for a non-Fermi liquid if it has no singular interaction, which comes from this term. The second term gives us a negative contribution to the mass, which by itself, it turns out, is always more negative than the Brighton-Lohner-Friedman bound of that geometry. So itself, it wants this, and it always has to fight against that term, and therefore you can and cannot, and we can tune this with this pair breaking parameter, make it or make it not superconducting. And when the pair breaking parameter tunes it to the BF bound, then we are at the superconducting quantum critical point. All of this, the saddle point, of course, can be shown to be equal to the superconducting solution. And the maybe last comment is, this was all done at 0 temperature. If you're now willing to engage into much longer equations and technical steps, you can repeat all these calculations at finite temperatures. The beauty is, I told you, there are conformal transformations of coordinates that connect actually 0 temperature and finite temperature transformations in the SYK model. And there's a similar statement that you can make mappings of metrics at 0 temperature and at finite temperatures on the enter de Sitter site. And they actually communicate exactly on the regime where we want to these two theories to be identical. So therefore, we managed to have a little bit longer proof, but along the exact same lines, where we could show that at finite temperatures, the system that approaches the transition temperature, it's a Gaussian theory only, that approaches the transition temperature is now governed not by entity space, but by this space that puts a black hole in the entity space, and has event horizon that's given by the Hawking temperature of the problem, and everything is it's supposed to be, and you get this. You get the black hole as a present of your analysis. It's not something you need to impose or put into the calculation. It is just the absolutely natural way of describing the system, and the stationary point of this one is the linearized Eliashberg equation. We also have done the phi-4 term, and there's nothing else but the square root of g u psi phi-4 term that comes out of the theory as well. If you wanted to go a little bit below the transition temperature, you can do that as well. So maybe this is a good point to stop. The message I wanted to bring across is, if you are a person who is not trained in holography and you had a tragic past of suffering through talks that you didn't understand and felt you should, there is a direct step-by-step way to understand these statements in simple models, which we could have solved otherwise anyway. So I haven't solved anything that I couldn't solve before. I will show you something maybe in the next talk where we go and use this machinery to say something new. But we have a mapping achieved, and that's what I find most interesting. We know now what this additional dimension is. The geometry is inherited from the critical state. That's why we have an entity space. A clever transformation hides the universality class and puts it into just the mass of the problem. The interpretation of the meaning is just the internal structure of the Cooper pair. So that's at least something that we can all work with, and maybe we can exploit and use or apply some of the wonderful insights obtained from this community with this additional insights. Thanks so much.
So I feel like